I'd like to start by thanking you so much for the invitation to speak. It's really a pleasure and an honor to speak to you. And I'm speaking to you from Toronto. So can we reduce the inevitable exposures to chemicals of concern? That's what we're going to ask and hopefully answer today, or at least ask. So to start with, I'm going to present my motivation. I contend that widespread exposures to anthropogenic chemicals, especially during fetal development, contributes significantly to human morbidity and mortality and is costly for society. Consider this graph where on the x-axis we have time, on the y-axis we have the number of people affected. We see that for exposures, let's take lead for example. It starts with identifying neurotoxicity in adults, then progresses to where there are poisoning incidences. Then and it is indeed that lead has been used in so many widespread applications, for example, as an additive to leaded gasoline and to paint. So you see subclinical effects in child populations. And then, if the use is sufficiently widespread for long enough, you experience a silent pandemic. This is the hypothesis proposed by Grandjean and Landrigan in 2006. It pertains to neurotoxicity, as they've described here, but unfortunately, it goes beyond neurotoxicity. The basis of the hypothesis is widespread exposure to different chemicals causing adverse effects to the point where there's this silent pandemic. Let me present two examples. The first is of pesticides that are used globally. Brodecker et al. Estimated that 385 million cases of unintentional acute poisoning occurs. 44% of those are in farmers. They lead to 11,000 fatalities annually. For those poisoned who are not killed, exposure to pesticides can lead to reproductive disorders, cancers, neurological disorders, and respiratory illness. Now let's take the example of PFAS in the European Economic Area. PFAS stands for per- and polyfluorinated alkyl substances used in so many different applications. Greta Goldenman et al. Did a study for the Nordic Council of Ministers a few years ago. They estimated that about 84,000 to 273,000 individuals are occupationally exposed to PFAS, leading to 12,000 deaths attributable to kidney cancer. Further, they estimated that moderate exposure occurs to 3% of the population, or 12.5 million individuals in the European Economic Area. The chronic and subclinical effects are low birth weight, and you probably know that having a lower birth weight leads to a higher probability of adverse effects throughout the life course, increased rates of infections due to the effect of PFAS on the immune system, and hypertension. There is a cost. There is a societal cost to these exposures and adverse effects. For PFAS, Goldenman et al. Estimated that the cost, the direct health costs, are between 12.3 and 41 million euros due to occupational exposure. That's on an annual basis. Non-occupational exposure, they estimated, costs between 52 and 84 billion dollars in the EU, in the European Economic Area countries. Add to that non-healthcare costs. Those costs would be for monitoring, for remediation, for destruction of PFAS. This is all related to PFAS. Those estimates range between 821 to 170 billion dollars in costs. Huge numbers. So to be really clear, if we're spending this money sort of mopping up the effects of exposure to chemicals, that means that we're losing money from other sectors of society. We're also losing productive members of society, and it's a terrible cost to be borne by individuals and families. Here's my argument. I argue that we are inevitably exposed to chemicals, including toxic chemicals. It arises because of in the Western world, our affluent society, and in the global South, for furnishing that affluent society. It also occurs because of our inability to sufficiently reduce exposures to protect populations. So why? Well, I submit that there are 4 reasons. Uncontrolled increasing production of chemicals and their uses, uncontrolled proliferation of the number of chemicals that are used, our inability to assess and then control this increasing production and number of chemicals attributable to lock-in, which I'll describe. So that's the plan of the talk. And then I'm going to end on actions and implementation for harm reduction. I use the term advisedly. We're not going to be able to eliminate harm, but we need to minimize harm. So let's turn to our argument, the explanation. So populations are inevitably exposed to anthropogenic chemicals. I maintain there are 3 reasons for this. First of all, it's just basic thermodynamics, and it's about fugacity, which I'll explain. Secondly, it's this increasing rate of chemical production and consumption, both total amounts and the number of chemicals. But it's important to note that we're not all equal, because we're not all exposed equally, nor do adverse effects occur equally. So turning to the first one, it's just basic thermodynamics, starting with fugacity. So consider a bottle of salad dressing, which I think most of you have experience with. So imagine that the salad dressing has an air, olive oil, and then a layer of either vinegar and lemon juice, depending on what you like in your salad dressing. The salad dressing is an analogy for the world that we live in. The air is the air around us, and it's also the air in our lungs. The olive oil stands in for our lipids. It also stands in for organic carbon, such as cuticles on leaves and the organic carbon in soil and in surface and ocean waters. The vinegar, the lemon juice, that's the water. It's both our blood and our interstitial fluid in the body, as well as fresh water, salt water in the environment. Chemicals will characteristically partition between air, olive oil, and vinegar and lemon juice. So for a non-polar chemical, take, for example, allicin from garlic, which gives garlic actually both antimicrobial properties and gives it the flavor. It's a semi-volatile organic compound, meaning that it's got a low but measurable vapor pressure. It will characteristically, because of thermodynamics, partition a little bit into the air, right? Because you can smell it. Most of it goes into the olive oil. And then, you get those wonderful, olive oils with garlic cloves in them. And then a little bit into the vinegar and the lemon juice, but not much, because this is a non-polar chemical. So now I'm going to explain what fugacity is. So for those of you who, for whom it's earlier in the day, or if it was the morning, probably most of you would be cradling a cup of probably hot coffee or tea. And you intuitively know that the warmth of the coffee or the tea inside your mug, you know that the heat is being transferred from the contents of your mug into the air, right? Because the air is colder. Of course, right? Heat goes from hot to cold, and temperature is the equilibrium criterion. And of course, heat moves from hot to cold. Duh. Well, the same is true for chemicals. They move from areas of high fugacity, where the chemical is stuffed into a product. Like, for example, the laptop from which I'm speaking to you. It's stuffed full of flame retardants to comply with the flammability standards. And then the air around and me, I've got a lower fugacity. So that chemical it just does move from high to low fugacity. And I want to take a moment to acknowledge Don Mackay, who was my supervisor, professor in chemical engineering at University of Toronto, who moved to Trent University. Don Mackay didn't come up with fugacity because it was Lewis in 1904. But what Don Mackay did was to popularize the use of fugacity to understand the movement of chemicals in the world. And he passed away just this past Friday. So continuing on that chemicals strive towards equifugacity. Consider this picture here. I took this in 2008. I know that because not only did I have more brown hair there, but also I bought my first TV. I had recently bought my first couch, and it was super exciting. Well, both the TV and the couch have flame retardants added to them to comply with flammability standards. In fact, I know which flame retardants were added because we did sampling. So those flame retardants, they're semi-volatile organic compounds, and they're inevitably leaving the TV and the couch to go into a lower fugacity environment, which is the air, but even more so, it's going to be the butter. The butter, why? Because it's got a very high organic carbon or like olive oil content. That's where these chemicals will preferentially partition. But it's also going to go into me because I have a lower fugacity than the TV and then the couch. I will inevitably dose up with those flame retardants that are found in my TV and my couch, the vehicle being either inhalation or the food I eat. It's absolutely inevitable, and those chemicals will preferentially partition into my lipids, including phospholipid membranes. So consider this crazy experiment that was done. I think this is Glenn Morrison, and I do know this is Charlie Weschler. They devised an experiment. This took place in Denmark, where Charlie Weschler is, I think he has a status at one of the universities there. This guy is obviously a control. Okay, so here's the experiment. They increased the concentration of two phthalates, phthalate esters, DEP and DNBP. They're both used as fragrance keepers, for example, in shampoos, or they masquerade as perfume in so many personal care products. So what they did is that they pumped in these two chemicals into this room. They sat there with only their underwear on, and then they peed into a bottle afterwards. And lo and behold, the concentrations of these two phthalates increased right after they were in the chamber. They were in this chamber for 6 hours. The other interesting thing is, and this comes from our work, we modeled this, and it's actually, no, it's the royal we, because it's former grad student Jacob Kaznichka. I didn't say that very well. Vaznichka, thank you. Okay, so here we have time. Here we have this is DEP and DNBP in the chamber over 6 hours. When the people leave, the concentration of DEP and DNBP go up by like 60 to 70% because the people are a sink. They're accumulating the chemical. In this circumstance, on their skin, they're accumulating this chemical. And when they leave with the chemical, and there's no longer that powerful sink. So those air concentrations actually go up, considering that there's a constant source. Okay. So show me some empirical data. So several years ago, Bill Nazaroff, I think Charlie Weschler was a co-author of this, calculated an intake to production ratio for the US. The intake they calculated through the NHANES biomonitoring data, and then they got production data. So this is bisphenol A, and then here we have a bunch of phthalates, including DEP and DNBP that we just spoke about, triclosan and methylparaben. This intake to production ratio is expressed in parts per million. So in other words, 1,000 parts per million equals 0.1%. What this graph says is that all those NHANES people, which are intended to be representative of the US population, have 0.1% of the production, the annual production of these phthalates in their bodies, because that's what they're peeing out. 0.1%. The number is lower for BPA. It's like a millionth, because BPA is typically used in polycarbonate polymer, which is a very tightly bound polymer. It doesn't release many of the monomers. But for methylparaben, it's almost 1-to-1, because methylparaben, of course, is used as a biocide in personal care products. It goes right on your skin. Produce it, put it on your skin, goes into your skin. So a few years ago, Li et al. Developed a very sophisticated model that looks at production tonnage and manufacturing and usage, intake from diet and so on, to look at exposure to tonnage. So this is exposure to tonnage ratio. Oh my gosh, it is 0.1%, the same as the back of the envelope calculation. So take home message here. Most of us are carrying around with us 0.1% of the production of a whole bunch of semi-volatile organic compounds. For this study, most of them are pesticides, but also you see solvents and construction materials and so on. So yeah, we're carrying around 0.1% of chemical production, but we're not all equal. That's an average number. So we've done work on social housing. These are social housing units located in Toronto. These are rental subsidized residences for low socioeconomic status individuals. They're built in the 1970s. We analyzed the air of 71 units using, and here's my show and tell. I know it's hard for you to see on the small screen. We used polydimethyl siloxane, just little pieces like this hung in the air. We were so dismayed. We found for a series of flame retardants, here we go, here are the flame retardants, here are the phthalates, and by the way, here's DEP and DNBP, the ones we just spoke about, 2 to 18 times higher in all the 71 units. We were dismayed and astonished. Oh, wait a minute, I forgot to tell you the comparison. Sorry. So here we have in blue the social housing units, and here we have in this orange color higher socioeconomic status homes located in Toronto. We used exactly the same measurement methods, the same PDMS, same lab, uniformly higher concentrations in the social housing than in higher SES housing. We went back to 41 of those units to measure pesticides. This time we didn't have enough money. We didn't have the money to look at higher SES. But what we did find, and we were so dismayed to find a whole host of pesticides, including, these are organochlorine pesticides. Here we have organophosphates, pyrethrins and pyrethroids that are current use. These are strobilins that are often used in, they're used as fungicides, for example, to treat wallboard, and then pendimethalin, which is used to treat tobacco crops. Okay, what's the take-home message here? 89% of the units had at least one pesticide, but here's our failure to be able to bring exposures down through chemicals management. DDT was banned in 1985, and we had detection frequencies of 30%. Lindane banned in 2001. Methoxychlor banned in 2005. So you can see detection frequencies up to 50. Well, you can't see the detection frequencies here. The air concentrations then of some of these are in the microgram per meter cubed range. Okay, so why? What's this failure? So let's unpack that. First of all, there's the growth in chemical production. So we took these data from Global Chemicals Outlook 2. We published it in Persson et al. 2022. The chemical production is normalized to the year 2000, going up to 2016. So this is the growth between 1950 and what year was it? 1950 to sort of current situation. There's been a 50-fold increase in chemical production. Chemical production is poised to increase another 3 times to 2050 for all the classes for which data were available, which isn't a lot. Total chemical industry. Here we have plastics, antibiotics, base petrochemicals, and pesticide active ingredients. The next point, so the last point is there's no controls on production. Next, uncontrolled proliferation of the number of chemicals. Zhenyun Wang and colleagues estimated that 350 substances are registered for use globally. 70,000 of those have been registered in the past decade. 30,000 are registered in emerging economies. The significance there is the limited capacity for emerging economies to have oversight over chemical production, over emissions, over worker protections. 50,000 of those chemicals have confidential business information, so we don't know what they even are, and 70,000 have ambiguous structures. This was a study done by Schumer in 1997. It's a bibliometric analysis. This is a log scale showing the number of known substances that goes up to, what's that number? 100 million from 1800 to the year 2000. In other words, this is an exponential curve in the number of known substances. Too many. So speaking of which, plastics, just plastics. Again, another study from Zhenyun Wang's lab. 10,000 substances are used in plastics, of which 2,400 could be of concern. 400 million tons of additives go into those plastics. And we can't assess. There's just way too many chemicals. We cannot assess them. So what we do know is a lot about very few chemicals. Let's take, first of all, ecotoxicity. So this is a bibliometric analysis by Christiansen et al. Here we have the number of chemicals along here, and this is a publication frequency. This is cumulative publication frequency. So if we look here, 50% of the publications refer to 65 chemicals. So that's half of the 130,000 papers that they analyzed referred to 65 chemicals out of 3,500. Those cadmium weighs in at 5.5% of citations. Next is mercury, arsenic, and then a bunch of pesticides. A study just published this year reaffirms that these are all chemicals. It's citations of all chemicals. The previous analysis was ecotoxicology. This is citations of all of the chemical literature writ all. They confirm 34% of citations. Here we have this red line percentage of citations were of 100 chemicals out of the universe of chemicals. This is the universe of chemicals. Here we have citations, number per year. 34% of publications refer to 100. And yes, most of them were the metals, pharmaceutical, and then coming in next, pharmaceuticals and pesticides. Only 5% were industrial chemicals. So here's an example. For EU REACH, 23,000 chemicals have been registered. 80% have yet to be assessed. So here's a great example of too many chemicals, cannot evaluate them. So take the case of this chemical, whose name I will not repeat. I won't even repeat the short form because it's just too long. So this chemical replaces PFOA, which was used in producing non-stick cookware. It's one of the PFAS. So what John Washington found, and his colleagues, that this chemical was distributed over, I don't remember the number of sampling sites, but they found, they did a broadcast analysis of soils, and they found that the distribution was cross-country at high enough levels. So that chemical has been produced at high enough levels so you could go out, sample soil, and you're going to find it. That means that a lot of that chemical has been produced. Yet, the EPA had no data on it. The European Chemicals Agency had acute toxicity data only. The European Food Safety Agency knew that it was not mutagenic. This is a great paper by Gold and Wagner saying, where are the data? EPA ComTox database. Say, look, none of this data, no quantitative risk assessment values, no hazard data, and yet high enough production to be found throughout the US and probably Canada. Okay, here's another example of our inability to, well, actually, this one is the inability to assess. The next example is the inability to control chemicals through a risk-based chemical management regime, which we have in Canada. These data are from the Canadian Health Measures Survey. In the dark blue, we have PFOS. In the light blue, PFOA, like the one we just, PFOA. And then the red is perfluorohexene sulfonate, PFHX. This is in the most recent survey, cycle 5, 2016 to 2017. Kids 3 to 5 years of age, all the way up to 60 to 79 years of age. And you see, almost 99% of Canadians have or had, right, because this was 2016 to 2017, measurable blood PFOS, PFO, and PFHX at low microgram per liter levels. This is microgram per liter, okay? Now, to put that in perspective, the US EPA proposed drinking water guideline, which they want to turn, which is being proposed as a legal standard, 4 nanograms per liter. So the levels in Canadians' blood, kind of 1,000 times higher in general terms. But note that in Canada, we were pretty quick, relatively speaking, to implement restrictions. PFOS was first. So this is the PFOS, right, in the dark blue. First regulations were imposed in 2008 with exemptions. Some exemptions came off in new regs in 2016. Further exemptions have come off in 2022. But this is an example of how, and of course you're going to think, well, only 8 years transpired between the first regulations and sampling, but over 8 years, 99% of Canadians are still weighing in at PFOS and so on at levels so much higher than the proposed drinking water guideline. That's a failure of chemicals management. And why? Because of lock-in. We would submit that lock-in is contributing to this failure. We published this last year, Jonathan Blumenthal et al., Time to Break Lock-in. Okay, so what is lock-in? I think you probably will relate to it most for fossil fuels. So lock-in is, why can't we stop using something when we know that it's a problem? Like, why can't we kick the fossil fuel habit? Goodness knows there's enough urgency about it. Why? Because we're locked into using fossil fuels. Well, we submit that we're locked into using some hazardous chemicals due to economic reasons. For example, having the infrastructure, the equipment, corporate organization. It depends on jobs, social attitudes, behaviors, and attitudes where we keep using a chemical, even though we may know that it's deleterious, or not everybody knows that it's bad for you. There's a technological lock-in. So you're locked into using that chemical. You have to change what you do. Oh, I've got a good example. Consider bisphenol A, BPA, and you know that an important exposure route, I don't know how much, is through what's it called? Through receipts where the printing emerges as a result of heating up the print, and that is enabled by BPA. Well, to change that technology and to get rid of the BPA means changing out all those point of service devices. You know, when you go and you tap your credit card and the receipt comes out, it means changing them all over. That's a cost. That's part of lock-in. We're locking into a technology that uses BPA in that example. And then there's political lock-in. That's a distribution of political power that favors coalitions and groups that promote the status quo. Won't go into that with fossil fuels because I think you see it pretty readily. But the same is going on with PFAS. The same has been going on even with lead. So, okay, let me present the timeline for PFAS to illustrate the problem of lock-in. In 1977, the 3M Corporation that was located, no, I'm not going to tell you where it's located, I forget. Well, it was in the States. I think one was in Minnesota, was producing 78% of the global supply of PFAS. And let me say the PFAS is used in many different applications, but one application for which it's received long-term exemption is to, as a surfactant during chrome plating. It was introduced as a risk management measure to reduce exposure to very toxic chromium-6. So there hasn't been a replacement, and PFAS had exemption. So that's just one example. Okay. So as far back as the 1950s, it might even go back before then, 3M had evidence that PFAS was causing adverse effects. For example, it found evidence of miscarriage in some female workers. And what they chose to do was to keep quiet about it and just rotate the women off that part of the assembly line. The evidence never came through. All right, that's another talk. Okay, so because of the evidence of toxicity bioaccumulation, in 1999, 3M, actually the US EPA brokered a voluntary agreement with 3M to stop producing PFAS. But the problem, and then following that, in 2009, PFAS was listed under the Stockholm Convention with exemptions such as that chromium plating application. It's also used in photolithography for computer chips. So the problem is that the Stockholm Convention restrictions, by the way, Canada is a signatory to the Stockholm Convention, so we imposed our own regulations. We actually did in 2000, regulated. The demand continued, and China grew the supply to meet demand. So Chinese production grew between 2002 and 2006 from 30 to 247 tons a year. So now fast forward to the present, where between 2017 and 2023, the Global Environment Facility that I'm now associated with. So this is a global fund administered through the World Bank. Countries like Canada contributes to it, and the US. We're giving money to China to reduce production of PFAS. Well, that's a cost that could have been used elsewhere. I mean, the money could have been used elsewhere. I put the couch here because PFAS was used in Scotchgard. Okay, so the key failure here was to restrict supply without addressing demand. Okay, so now let's move to actions and implementation for harm reduction. So 5 points. I'm going to start with hazard and not risk assessment. So Canada, the Canadians Chemical Management Plan works on risk assessment. It's absolutely works on risk assessment, which you probably know is that you figure out what exposure you're getting, you figure out what the hazard is, and you say, is your exposure high enough to cause a risk? And if it's high enough to cause a risk, then we're going to impose risk management measures. But it doesn't work. It doesn't work because of lock-in. That's the key problem. So why doesn't it work? And here I just have to go back, I think. It's because for the exposure to reach a high enough level, actually, I'm going to go back. For exposures to reach a high enough level to trigger risk, that means that industry, the economics, the social, all these factors have been going along for long enough that you can't easily break the lock-in. That's the failure of risk assessment. By the time you reach a point of risk, you're already locked in. That's why you need a hazard-based approach, which says, thou shalt not use these chemicals because they're too intrinsically hazardous. We're not going to wait for those chemicals to reach high enough levels in the population. We're not going to do that. So under the Chemicals Management Plan, and actually it's the update to CEPA that was passed recently in Parliament, we have the schedule of toxic compounds that is derived from a risk assessment. And I maintain that that suffers from lock-in, very hard to bring down exposures due to risk management measures. Too little, too late. I am pleased that under the Chemical Management Plan, there is a list of high hazard chemicals that do not have to go through the risk assessment process. We're on the right track. I would like to see us move more towards the model in REACH, which is the European Union's Chemical Management Plan program and legislation, where they have hazard classification. If it's carcinogenic, mutagenic, or has reproductive toxicity, amongst some others, it's out, it's on the high hazard list. The next solution I suggest needs to be chemical simplification. We talked about the proliferation of chemicals and plastics. So not only does this proliferation of chemicals, like we said, well, you just can't even study them all, it's an impediment to circularity. So you cannot recycle chemicals with so many additives. Right now, so there's a movement to reduce the complexity, for example, of PET, which is the one plastic that's achieved up to 35% recycling rate in the US and Mexico, don't know about Canada, to limit the number of chemicals in that plastic so that it can be recycled, but you can also assess it. Well, the vehicle here, I hope, will be the new plastics treaty that is currently being negotiated. The meeting in Nairobi is coming up. That's INC3, the meeting in Nairobi to hammer out some of those details for the plastic treaty is coming up in November. INC4 will be held in Ottawa in April, the end of April. It would be an intergovernmental instrument that ratifying countries would sign on to, implement their own legislation. So by doing so, it would become binding, right? When it becomes legislation, then you have to do it. So I'm looking forward to the plastics treaty. All right, next, the cap on chemical production. So we came out with this, with this idea, big new idea, to put a global cap. Well, first on emissions, but then I say a global cap on production. Let me describe what I mean by a global cap. So consider this graph over here, which is global carbon emissions from fossil fuels that you know is going up. This is 1900 to 2010. We just know it's going up and it's depressing. Well, through the United Nations Framework on Climate Change and then renegotiated Paris Accord, at least there was an understanding that you can't have activity-based limits. You need a fixed cap. An activity-based limit means you can have so much amount of greenhouse gas emissions being emitted out of, oh, let's just say a car. The problem is that we're driving more and there are more and more cars. So activity-based limits don't work. The world, the planet, knows that you need a fixed cap on all production, not according to activity, not according to, well, apportioned according to country. So the big idea is that we need to be implementing or thinking about how to implement a cap on production of chemicals. We have to manage lock-in. So one way to manage it is to have hazard and not risk assessment, because you try not to become locked in at the get-go. But once you're there, at least broadening the scope of regulations so that the regulations consider both supply and demand and how they're intertwined. You need to engage stakeholders early for comprehensive plans, transition plans, for example, the just transition, right? From transitioning from fossil fuels. But overall, we need to promote long-term proactive thinking, which is why I'm so happy to be speaking to you, because I hope you'll embrace this. We need to prevent lock-in before it happens. Safer alternatives, which are not always possible. And as I say, hazard and not risk-based management. And what's the vehicle for this? Well, I'm hoping that we can use some existing instruments like the Stockholm Convention on persistent organic pollutants. I recognize that the Stockholm Convention, oh, I forgot to, is it like 20 odd chemicals? It only pertains to persistent organic pollutants. Very challenging to get a new persistent organic pollutant registered under Stockholm. Very high weight of evidence required, but it is a multilateral environmental agreement. There are others, there's Basel and Rotterdam. In December, the third meeting will take place of the new science policy panel on contributing to the sound management of chemicals and waste and pollution prevention will be held. Third meeting. That intergovernmental forum for discussion doesn't have a binding treaty attached to it, so there's nothing binding participants, but it is a forum, at least from countries globally, to sit around and discuss ideas for environmental protection for the wide range of chemicals. So the last point I want to say is that fundamentally, a lot of these solutions come back to us, not as individuals and as societies. I don't want to put the burden on individuals, but for those of us who can, I think we need to be advocating for both precaution and the idea of sufficiency. So this is a paper from Vitamin et al. In 2020, where none of us want to be in poverty. And of course we want to lift people out of poverty. But we also have a situation of dramatic and really obscene, in some cases, overconsumption, which is environmentally unsustainable. They've done analyses to show that affluence is really driving so much of the chemical pollution. Consumers in wealthy countries, producers in low and middle income countries. We need to figure out and move towards sustainable lifestyles that are less consumptive. That's the bottom line. We are not going to green chemistry our way out of this. We cannot find safer alternatives for all chemicals. For example, biocides. We need to reduce our expectations in the wealthy world. And some of that comes out of redefining what we mean by well-being and having a well-being economy. I want to end then with this wonderful quote from Thomas Homer Dixon, who wrote Commanding Hope. He published it in 2022. A commanding hope that's honest about the dangers ahead and astute about the strategies we should use to face those dangers, and one that powerfully motivates us. Let's not aim for what's merely feasible and falsely hope that it will be enough. With commanding hope, let's aim for what we'd all consider to be enough, a future in which our children and life on this planet can flourish. With that, I would like to acknowledge the following and open up the floor for questions.